Hi there, my name is June and welcome to another video of Learning with Levi. In this video, we'll be helping you decide which way a reaction will go with certain conditions, whether that's SN1, SN2, E1, or E2. We've also started doing a podcast format for those who'd like to reinforce these concepts on the go, and I'll link those down below. So we learned from previous videos that if a reagent acts as a nucleophile, substitution will occur. If a reagent acts as a base, elimination reactions will occur. What we need to do is to figure out if a reagent is acting as a nucleophile or a base, and then from there we need to determine if it's a weak or strong nucleophile, and the other option is a weak or a strong base. So if we look at the periodic trends, nucleophilicity and basicity increases as you go left of a row. Now if we compare oxygen and fluorine, fluorine is more electronegative than oxygen. Fluorine can stabilize the negative charge better because it's more electronegative, thus it's more acidic. Just FYI, as you go right, the more electronegative the atom is, the more acidic it is. Now, if we look at columns, the periodic trends for columns, as you go down a column, size, acidity, polarizability, and nucleophilicity increases. Now, if we compare bromine and fluorine, bromine has a larger atomic radius, meaning that the bonding electrons are further away from the nucleus. The electron density of a larger atom is more polarizable and thus more able to stabilize the negative charge better. That means as you go down a column, it becomes more acidic, and the bonding electrons are held more loosely, thus it's more available to be a nucleophile, and that is why nucleophilicity increases as you go down a column. Now with this in mind, let's mention some examples. Now if we look at this chart, in the middle it says, what is this reagent acting as? And now if you look to the far left, it says nucleophile only. Some examples are halides and sulfur nucleophiles, which act solely as nucleophiles. These are very polarizable, making them strong nucleophiles, but are weak bases. And as we know, the more basic the nucleophile, the more likely the reaction is to turn to an elimination reaction. If these are your reagents, you'll most likely have substitution reactions. Now if we go to the next path where it says strong base only, an example is tert butoxide. Strong bases are used to help push a reaction to E2 over SN2. That's because the tert butoxide is sterically hindered and thus will not be able to attack the nucleophile, the electrophile from the backside. Now if we go to the next path, it says strong base, strong nucleophile. Some examples are hydroxide and alkyl oxides. These are used in SN2 and E2 reactions. Hydroxide and alkyl oxides are good nucleophiles because they can donate a pair of electrons. They are also good bases, and with SN2 reactions they require a strong nucleophile, and E2 reactions require a strong base. With SN2 reactions, because they require a strong nucleophile, it's because they are part of the rate limiting step. With E2 reactions, they require a strong base because the base is part of the rate limiting step as well. Now if we go to the last path, it says weak base and weak nucleophile. Some examples are water and alcohol, and because they are weak bases and weak nucleophiles, they are often used for SN1 and E1 reactions. Now each of these reagents, whether it's solely a nucleophile, solely a strong base, strong nucleophile, or a weak base, weak nucleophile, they have a potential to react with primary, secondary, or tertiary substrates. In the case where the halides and sulfur nucleophiles act solely as nucleophiles, for primary and secondary substrates, SN2 will be favored. Why SN2? That's because the nucleophile must be able to get into the substrate from the backside. Primary and secondary substrates are not as sterically hindered for the nucleophile to attack relative to the tertiary substrates. For tertiary substrates, SN1 will be favored. That's because the alkyl groups will help stabilize the carbocation through the inductive effect, as well as hyperconjugation. In the case where you have tert butoxide acting solely as a strong base, this path right here, for all types of substrates, primary, secondary, or tertiary substrates, E2 reactions will be favored. Again, because SN2 cannot proceed through a bulky nucleophile, the reaction is pushed towards E2 reactions. In the case where we have reagents such as hydroxide and alkyl oxides, which are used as strong base and strong nucleophiles, for primary substrates, SN2 will be favored over E2, meaning that the major product will be SN2 and the minor will be E2. Unless a bulky base is used such as tert butoxide, this will help push the reaction to favor E2 over SN2. For secondary substrates, E2 will be favored over SN2 due to steric hindrance, meaning that the E2 product will be the major and SN2 will be minor. For tertiary substrates, E2 will only be favored due to steric hindrance. You cannot attack the backside of the electrophile, but it can abstract the beta hydrogen needed for E2. Tertiary substrates also cannot undergo SN2. In the case where you have water and alcohol as weak bases and weak nucleophiles, for primary and secondary substrates, no reactions will occur because it would proceed way too slow. For tertiary substrates, SN1 will be favored at low temperatures. At higher temperatures, E1 will be favored. Now, as a reminder, you want to make sure that you're addressing the regiochemistry as well as the stereochemistry part of the reactions. Now, if you look at the bottom right of the table, we have these helpful tips. And then, as you can see, with SN1, you want to get a mixture of retention and inversion products. Because the carbocation formed at the SN1 reaction is flat, you can attack it from the top or the bottom, giving 2 enantiomers, which we call racemization. For SN2 reactions, because the nucleophile attacks the backside of the electrophile, it results in the inversion of configuration at the carbon atom being attacked. For E1 reactions, it will always follow Zaitsev's rule, which states that the more favored product will be the more substituted one. And for E2 reaction, Zaitsev's product will be preferred over a Hofmann product unless a bulky base is used, which will then form the Hofmann product. Also, the beta hydrogen must be anti to the leaving group, meaning 180 degrees from each other, also known as anti-periplanar. With that concludes the video. And down below is a preview of the SN1, E1, E2 reaction study package, which will all include the 24 study aids which we've used in the previous videos, all conveniently in a one big PDF, and I'll link those down below. Hit that like button, that subscribe button, support the channel, and share it with your friends who need help with organic chemistry. In the next video, we'll be going over addition reactions. I'll be putting more videos down below, so let me know in the comments what you'd like to see. Social media links are down below, and as always, remember, you gotta go.